Good day, everyone, and welcome to this Lightbend podcast and video cast for today. My name is Oliver White, Chief Storyteller at Lightbend, and I'm sitting down with one of my favorite colleagues, Hugh McKee. Hugh is our Akka developer advocate at Lightbend, as well as an O'Reilly author, and until very recently, a frequent conference speaker. We are sitting down today to talk about Akka, especially some of the new features released in Akka 2.6.4, which has some very interesting updates. Hugh, thanks for joining me today. How are you holding up being at home after flying around the world something like 10 times last year?
I definitely have a bit of cabin fever. I had a very heavy travel schedule right now. I would have been right in the middle of it. And, it's gone. I've been trying to unravel all the bookings and everything that I had queued up. But
yeah, that's a struggle.
So I was thinking of tweeting. I just miss everyone.
Mm-hmm.
I love going to conferences. I love speaking at conferences. I love talking to other people at conferences. I really enjoy mingling with the speakers that you run into at all the different conferences, and just traveling in general. I really do enjoy that, and so I do miss everyone at this point. But
yeah, there's little replacement for the in-person feel, right?
Yeah, especially in like giving talks, and when you can see that you're getting through to some people. You always see people that this talk isn't interesting to them, and maybe this talk is maybe annoying them. You can see that when you look around the audience. But when you see the people out there that are kind of sitting forward in their seat, or they're kind of shaking their head up and down when they're agreeing with you on something, that's the best. So it's like, there's some really good solid participation happening in the audience, and that you feed on that as a speaker.
Yeah. Well, I'll be nodding for you today.
Yeah, okay. So at least I can see you. So
play my part. I'm wearing my happy hacking Akka shirt.
Oh, that's
today.
right. I should have worn a nice T-shirt.
You look good in black.
Yeah.
So let's talk a little bit about Akka 2.6.4. I think you were the one to say that, wow, there's so much stuff packed in here. It almost seems like 2.7. And one of the biggest things I think we've discussed a little bit already is a feature called reliable delivery. But I wanted to, if you're willing, take a bit of a step back before we get into that and talk about message delivery in distributed systems in general. Just kind of, set the scene for us. If we've been building kind of monolithic architectures for the last 15 years, what does messaging look like in those systems versus these distributed systems of microservices? When messages are coming in from users, messages in between services and databases, what's changed? And maybe we can just set the scene there a little.
Yeah, this is by far one of my favorite topics.
I know.
By far. So the problem is shutting me up on this. I've written about it, and I love thinking about it. The challenges and the ways you solve these problems of communicating in distributed systems are extremely interesting, I think. And one of the biggest challenges, I think, going from, say, a very nice, comfortable, monolithic world into a distributed world is that, in a monolithic universe, you basically got all your code running together in the same process. And so one object, one instance of a class is invoking a method of another instance of a class in an object-oriented system. Or if you're in more of a functional system, one function is invoking another function, those types of things. And it's all in process. And you can do asynchronous and so on, so that the invoker is not waiting for the thing that was invoked to finish, or you can do synchronous processes. But it's all, the one major thing that you don't have to deal with is communicating between processes. So I don't have a good analogy for, I always like using visual analogies, but I really don't have a good analogy for what it's like, when we write code that runs within a process. other than, it's like thinking in your own head. It's like you're talking to yourself in your own head. Because, and maybe that's it is a good analogy, because if you say you're, I think we're all a little bit crazy in this business, and in this tech business. So we do a lot of, maybe we don't talk out loud, but maybe we do, when we're thinking deeply about a problem, but it's a conversation that you're having in your own head. But everything changes very, very quickly when there's a conversation between two processes. And this is where the fun begins, because what I like to, is a mental exercise, and as a way to explain this, is say that it's the dialogue between you and I, for example.
Yeah. Okay.
We can think of us, we're two different processes that are running, and we're talking to each other over a network. So that a flow that we can agree on, we're programmed, the two of us, to handle a very, very specific flow. So say something happens, some other external force triggers you to perform some action.
Okay.
And so you've made a state change. You
send me a message saying,
well, somebody else did, not me yet.
So somebody sends me a message that says, hey, get on the Zoom call with Hugh.
Right. Like say you get a reminder, right? Something like that. So you've kind of made this state change that you need to contact me. You need to talk to me. So that's kind of step one. Step two is you do send me a message. And then step three is I receive that message and I react to it in some way. And this could cause some kind of a permanent, let me add this to the state change, a permanent state change to me. And then after I've done that, maybe you've asked me to do a piece of work, which involves me, say, writing it down, which is kind of recording a permanent change that I've made. Then I send back a response to you saying, yep, I did what you asked me to do. And then you make another change. It's like, okay, you've recorded, yep, Hugh did what I asked him to do.
So my state has changed.
You're right. And your state changed twice. First you to call to action, then to communicate with me. That's 2. 3 is I did something. 4 is I sent back a response to you. And 5
is I acknowledge that reply.
Right. You got it, right? So, it's like when we look at this, all right, it's a 5-step process basically. And we go, all right, we're moving from a very comfortable monolithic world, and now we're kind of thinking in the same way that you're invoking me, the way you went and call a method from one object to another inside the monolith. Now you're an object, I'm an object, but we happen to be distributed across the network. So we've left that comfortable world because
so we're not in our own heads anymore.
Right, we're not in our own heads. We're not in this comfortable process world anymore. And the big question is, what's going to go wrong with this process? Because
so there's 5 steps, and at almost any of those steps, something can go wrong. And what are we going to do? What do we have a plan when something will go wrong? Because it usually will.
It will, right? And that's one thing I always say to people, especially when we're looking at doing things in the distributed world. It's not a matter of if it's going to go wrong. It's a matter of when it's going to go wrong.
Right. And
you just have to face it. And this is to me is the fun part, right? Because we can fix this. We can solve this problem. But this is where things get really interesting, though, because since you're the thing, the thing that's initiating the action, our intuition says, well, you're going to send me a message, right? So this is could be a challenge, because what's going to go wrong? Well, the first obvious thing is the communication channel between the two of us is cut off, or you just can't communicate with me for some reason. You don't know why, but you've got something that you need to tell me, and I'm not reachable.
So one problem is that I've got a message to send, but I can't. Another problem can be I've got a message to send and I send it, but something goes wrong before you receive it.
Right.
Okay. So those are two challenges. Okay.
Right. So from your perspective, what you're sitting there is you got a message to send that hasn't been sent. Right. Now, like what you just said, though, is that it could be that you sent the message. I actually did receive it, but you don't know that I received it, right? Because, you're waiting for a response from me.
Mm-hmm.
And maybe on your side, say we're doing this like the good old HTTP RESTful way, you're going to get a response, you're going to get a timeout. And then when you get a timeout, it's like, I don't know what happened. This is you, right? I don't know what happened. But it could be at least a couple things. One is I never got the message is one problem, or I did get the message and I actually did react to it. It was like, one, you decided to send me a message. Two, you sent me a message. Three, I did get the message and I processed it, but I couldn't do four. I couldn't get the response back to you. Or the other scenario is I never got the message. One, you decided to send me a message. Two, you tried to send me a message and the message never got through. Now, so in this kind of a situation, from your perspective, you're either going to get a response from me or you're not going to get a response from me. But now when you don't get a response from me, when that happens,
what do I do? Yeah.
What do you do?
Right? So there's a contingency plan for each stage, or rather there should be. Mm-hmm.
Yeah. And as the
because sender, if I send you a message if I send a message and I'm not sure that you got it, for me to send another 500 of the same message at the same, in the next moment would not necessarily be helpful, correct?
Right, because if I'm having a problem and I do receive all of the messages that everybody's, say where I live at, the server that's handling all these incoming messages can get overwhelmed with a storm of messages, maybe retries or something. And so on my side, I'm getting overwhelmed with requests that I can't handle for some reason. And so that brings up the use of a circuit breaker. Let's break the circuit between the two of us. So every time you try and send a message, it's just going to pop right back to you and say, nope, I can't send it because the circuit breaker is open. Okay. So, but then, all right, you still got this message to send. You have to get it to me.
That's right.
You can't just throw it away and dismiss it. You've got it. The ball's in your court.
It's a tough job.
So which is a good point, because there's an alternative for this kind of a flow that I'll get to in a little bit. But let's just walk through this a little bit. So you're sitting there with a message that needs to be sent, but you can't send it right now. Now, I'll bring up that you're in a vulnerable position, because if something happens to you and you shut down and have to restart, you need to be able to remember that you've got that message to resend. So if you don't do this, if you don't somehow record that you've got a pending message, and when you fail and come back up, if you don't recover that, you've lost the message.
And this is where we use an event log, I presume.
Potentially, yeah. Right. Or some way of, before you send me a message, one of your steps is you got to save the message as a pending message, and then you got to try and send it to me. So now your burden of responsibility is trying to send me a message, having to deal with circuit breakers, and also making sure that you're recoverable, that you can stop and start again and pick up where you left off and not drop any messages. Because what we're trying to do is guarantee message delivery here. Right. So that's a lot of burden of responsibility for you as a sender.
It is. And I was just trying to get rid of this message just a few moments ago, so.
Right. And it's one of those things like, yeah, you can set this up and doing like HTTP and writing an HTTP client, which is what you basically are. And I'm kind of on the HTTP server side, for example. Writing that code is dead simple. And doing some kind of RESTful, request to send me some JSON, it's dead simple. That's the easy part. Yeah. And you can set this thing up and go into production, everything's working. And when something goes wrong, then you stop dropping messages and these messages can't be dropped. And it's like, oh man, we got a major bug in our system that we have to fix. And then things start to get fun. And it's not just coming up with things like a circuit breaker, which is relatively easy to set up as well. There's great tools for that. But it's also the whole persistence of pending messages that need to be sent.
Mm.
Now, on my side, I receive a message, and then say I do some kind of processing on my side, and that's a state change on my side. I'm doing maybe doing some kind of my own little transaction, database transaction or something on my side, and then I send you back a response. Well, I've got some responsibility as well. That, all right, I got the message from you,
Mm-hmm.
and I'm trying to send you a response, but then I can't. So, what do I do?
Mm.
And so an easy kind of, the easy way that works is that I just go, well, I couldn't send them a response. And I'm not going to do anything else, right? So, but I know that you're going to eventually send me the message. You're going to keep trying. You're going to keep trying to send me the message until I acknowledge that I got the message. So
Okay.
what that means is I know that, well, I did what he asked. I did what Oliver asked me. But I need to be prepared because I can't return the response. There's a possibility that I'm going to see that same request come through from Oliver again.
Mm-hmm.
So I need to be able to do something where if I see a duplicate message that my operation is idempotent, meaning if I get the same message multiple times, the result doesn't change.
Mm-hmm.
And a common approach is that I can filter out duplicates. When I see an incoming messages, I'm filtering out the duplicates or something like that. But that's something of my responsibility is that I need to handle the duplicates.
So if I continue sending the same message over and over, and on your side, you're able to deduplicate them and it doesn't affect the state of the further processing, am I also kind of stuck in a loop where I'm also not able to do more work at that time because I'm still sending you a message that I have no idea was received?
Right.
So
and you're stuck
that
loop. Yeah, you're stuck in that loop until you get a successful acknowledgement from me, and until you actually make that final step 5 state change. Yep.
Mm-hmm.
Here, you receive the response, but then you maybe perform a database transaction operation that records. Yep, got the response, done.
Mm-hmm.
We're good. That the work was completed. So you could receive the response, but before you actually perform the operation, you could fail. Right? You're still in a precarious position until all 5 steps, that whole loop is successfully completed and is done. Right? And until that happens, things can loop. Where your responsibility is you have to keep retrying over and over and over until you get a successful acknowledgement and you react to that successful acknowledgement.
Okay.
So this is kind of the worst case scenario in this type of an approach. The alternative that you're leading to is that instead of you pushing me the things that I need to do, what you do is you somehow record. You get some action and you record. Yep, I've got this work that I recorded, and the information is in a state that means I've got to do something with it.
Mm-hmm.
So it's kind of in that you're just stacking them up. It's like you've got a stack of papers on your desk, and the outbox, and I got to keep pulling from that outbox to do the work I need to do. So this shifts the responsibility a lot.
So push versus pull.
Exactly.
Mm-hmm.
Right.
So now you're coming to me and saying I can do more work, and I'm collecting work for you or someone else to do.
Right. Now, and there's kind of one of the greatest approach is kind of the passive pull from your perspective, meaning that your only job is this request came into you, you record it, you're done. Mm-hmm. That's it. That's all you have to do.
It sounds nice and easy.
Yeah, for you, right? So, but my responsibility is a little bit more because now I'm responsible for pulling the pending work that I need to complete. And in that kind of scenario, I need to be able to record, yep, I pulled something, like I pulled a message from you, from your queue. I processed it. and then I record the fact that I processed it,
Mhm.
so that when I fail and I come back up, I know where to pick up where I left off.
Okay. So
So
basically
that,
recording every state change.
right.
Mm-hmm.
And this is very much like a Kafka consumer,
Mm-hmm.
where the consumer is offset driven. So you got a stack of, you're building up a stack, and say the stack is 150 high, and I'm currently pulling from 125. So I
Mm-hmm.
grab 125, I process it, I record, yep, I did 125. And then, boom, I fail.
Mm-hmm.
When I come back up, I look and go, oh, the next thing I need to pull from Oliver is 126. So then I start picking up where I left off.
Gotcha.
This pull approach, so the mechanics is a little bit more responsibility on my side, but not horrendously complicated. The main thing is, typically dealing with reliably persisting the offset
Mm-hmm.
that
Okay.
I completely.
Reliably persisting the offset, yes.
But
I
it's
like that.
my responsibility, not
Mm-hmm.
yours. So the dynamics here changes a lot. Your job is really simple. Your only responsibility is say structuring the work that I need to do in some kind of a queue or some kind of a log or something. And that's what event sourcing is. You're putting things into an event log.
Mm-hmm.
And I'm consuming those events as fast as I can from you, but it's my responsibility to consume those events from you. It's not your responsibility to push them. And this gets into reactive streams.
I was just going to ask if this is where we were
Yeah.
heading. Yeah. So
Yeah,
this is back pressure at work.
Right, because reactive streams really is simple in that my responsibility is to signal to you, I'm ready for more. You give me another message, Oliver, right?
Gotcha.
Where I actually signal to you that it's okay to send more messages. The event log is kind of a buffer in between those two things, in that you're not held up waiting for me to ask for the next message on your end, because what you're doing is you're just throwing things in the log as fast as possible, and you're not waiting for me to catch up. And this is this is eventual consistency, where the idea is I will eventually catch up to you.
Mm-hmm.
I'm not, I'm always at least a little behind, but I could be far behind because maybe I stopped for some reason, or maybe there was a problem with the network between us and I just couldn't pull anything from you. So I'm falling behind. But when I do come up, as fast as I can, I'm consuming the pending work and going. With a pure reactive stream, you may have messages to send me, but you have to wait for a signal from me where I say,
that you're
I can
here to ready and willing to go. Gotcha.
Right. And this gets into the features in the reliable delivery. And
yeah, let's talk about reliable delivery. So it's almost a misleadingly simple term, reliable delivery. It kind of sounds like apple pie with vanilla ice cream or something, but I mean, so this is why I wanted to set the scene a little bit, because for people that are kind of new to distributed systems, just understanding how much more complex that communication between both from outside and from within the system between the services starts to get. Mm-hmm. So when we say reliable delivery very kind of nonchalantly, it's actually going through a ton of work in the background. So let's go get into reliable delivery now. I think we've got a good foundation here.
Yeah. And so it was interesting, as you mentioned at the start, about, okay, these features came out. It really is all focused on Akka typed versus Akka classic, which is, strongly typed messages between actors with Akka type versus not strongly typed messages with Akka classic. But I was in a meeting with the Akka team. We meet about once a week usually, and it's on a Monday, and they say, we're gonna release 2.6.4 on Friday. Oh, that's cool. What's in it? And you go, oh yeah, it's reliable delivery, and what are some of the other ones? It was reliable delivery, sharding, and distributed pub sub. You know, and it's like, and they talked about reliable delivery. Yeah, there's point to point, there's work pooling, and then there's sharding with reliable delivery. And I'm going, and you guys don't mess around. They said something like that. It's like, where did all this come from? This was like, doesn't feel like a tick release, you know, point 0.4 release. It was like, this is more like a 2.7 release or something. But hey, that's what they did. And, yeah, and so they really put out a lot of really nice stuff in this release. So with point to point, so reliable delivery, it has point to point, work pulling, and sharding. Those are three of the big patterns that are in it.
Quick, just real fast though, Hugh. I mean, everybody who uses Akka is pretty aware at resiliency and elasticity and general reliability. What did we not? Were we not reliable for message delivery before, or is this more humility from the Akka team?
Well, messaging, even there, is really interesting because, you know, message semantics fall into three categories: right? At most once, at least once, and exactly once. Okay. And I like calling it at most once, maybe once. Maybe you'll get a message, but maybe you'll lose the message. At least once means once or more, that you will get the message, but you have to be prepared that you're going to see that same message more than once. And then exactly once is the nirvana, which was what we would really like to do, but in almost all cases, it's like trying to break the speed of light. And, you know, so there's a lot we can talk about there. But with actors, the messaging between actors is very much like the messaging when we're texting. It's at most once. You send me a text message, you know I might not get that message. You know, it might not get delivered for all kinds of different reasons. It's just, we understand that. So we deal with it. You know, think of us as two actors and we're trying to communicate with each other, and you send me a message, you never hear back from me. Well, that's your problem, right? You know, what are you gonna do about it? Well, maybe we just drop it, or maybe you try to send it again, and maybe try a few times and then you give up. And people often freak out when they first hear about this with Akka, when they first start learning about Akka and messages between actors. It's like, well, I don't want, you know, maybe losing some messages. That's a pain. You know, I want messages to go through. I want exactly once. You know, everybody wants exactly once. But sorry, you know, you can't go faster than the speed of light. At least we haven't figured it out yet. And exactly once is a matter from the perspective of the producer or the consumer. With exactly once, when it's all said and done, and there's a lot to talk about here, but let me just say briefly, the consumer never sees a duplicate, because somewhere just upstream of the consumer is some form of deduping is happening. There's a few circumstances where you can get away from that, but you got a situation where no matter how hard you try, just because you and I are across a chasm of a network, doing exactly once just ain't going to work. You know. So it's a matter of perspective. So the one that is easy to implement is once or more, at least once. At least once. And I always say at most once, at least once. You always have to think, okay, which one is it? But
you're thinking about it too much. That's why.
Yeah, but you get the message for sure. You will always get the message, but the deal is you're going to get some messages more than once, and that one's technically much easier to implement as far as reliable delivery.
Okay.
So
you'd rather have more than less. Right. So with reliable delivery, you mentioned point-to-point, work pulling, and sharding. Let's talk a little bit about those.
Yeah, so with point to point, and there's some really good documentation. And that's why I keep turning my head. Sorry, because it's on
No
another
worries.
screen here. There's some really good diagrams with it as well. But it's like, now you and I are actors, and we want to make sure that messages get sent.
Mm-hmm.
So the idea is that we're going to work through some collaborating actors that we get from Akka. So there's it's called a producer controller and a consumer controller.
Okay.
So say you're the producer and I'm the consumer. So on your end, it's not just a simple actor sending a message directly to me. You're routing the messages through a producer controller.
Okay.
Okay. And then on my end, I collaborate with a consumer controller. And it's a pull versus a push approach. So
so the producer controller is pulling from me, the producer as well, or is it the consumer?
Well, the producer controller is signaling you when it's okay to send a message.
Okay, so requesting a send. So we can call that polling, I guess, but well, maybe not. But
it's the reactive stream semantics, right?
Yeah.
Because the reactive stream semantics is that the producer is no longer in control.
Mm-hmm.
The producer is kind of the subordinate player in this whole little theater, this play, in that you have to wait until somebody signals you, all right, I'll take your next message.
It's like letting people into a club where there's a maximum capacity.
Yeah, my club days are long
Not that I've
gone.
been to a club in some years, but
Yeah, well, it's been even longer for me, but yeah, I know what you mean.
The golf club. You're in Florida.
Waiting for a table at a restaurant.
Okay.
Right? All right, so something like that. But in any case, you can't send a message until your local producer controller sends you a message saying, all right, you can send me the next one. So then you send the next one. And then the producer controller and the consumer controller collaborating with each other. And, so you got the signal, send the next message, you sent it, and the producer controller tries to get that message over to the consumer controller.
Mm-hmm.
And then ultimately I get the message and I process it, and I can say, and then I can signal the consumer controller, all right, I'm ready for another message. And then the consumer controller sends it over the wire to the producer controller, and producer controller sends it to you.
So let's imagine that there's lots of consumers and not just you. Is it important for example, with Akka typed, perhaps the message is intended only for you as an individual, as a specific consumer. Is that something that happens as well?
It is, because it is point to point.
Okay, so this is you have an entity ID or entity key or something like that. So this has to go from Oliver to Hugh. If it goes from Oliver to Jerome, then this process is failed.
And it won't, right?
Gotcha.
Yeah, that's a completely different communication channel.
Gotcha.
That would be something you would have to set up that's totally different from this point to point.
Understand. Okay.
Flow.
I was hoping that's what point to point actually meant. Just
yeah, and I'm hoping I'm not butchering this, because I've been studying this a lot and it is new to me. But that's the idea. It's you're an actor, I'm an actor. We're using these intermediate controller actors, producers, and consumers, because you're a producer, but you're routing things through a producer controller, and that producer controller is kind of sitting on the edge of the the node that you're running on. It's the one that talks over the network.
Gotcha. Okay.
And it's the controllers that talk to each other over the network. So I have a consumer controller that I started up, and we initiate this flow, right?
Okay.
And it is this point to point.
So does this sounds like, in terms of push versus pull, or passive pull, how does this relate to the work pulling pattern? Is this part of that as well, or is it related?
It's kind of the foundation to it, but work pulling is a little more involved. And with work pulling, we're still doing the same kind of a flow, that the consumer is signaling to the producer that it's okay to send a message. And ultimately, say you're the producer, you'll get a message from a controller. It's called a work pulling controller, but it's very similar, saying, it's actually the message is request next. You get a request next message. And that's your signal. You can send a message. Now, before we get too far, just think about that for a second, because you can't send a message until something tells you you can send a message. So what are you going to do upstream from you? Like, what's actually triggering you to have a message to send? The buck stops here in a way, type of thing. Where does the
where am I getting my messages from?
And what do you do upstream from you, say? It's like, because basically it's like when you get something to do, you're not done until you get a request next, and then you feed the message into the system, right, into the flow, and it goes through.
And for this form of, so for work pulling, does it, compared to point, the consumer may not necessarily need to be a specific consumer, or is that rule still kind of applied?
No, that's the big difference. With the work pulling,
be any actor out there.
It could be multiple workers consuming from you, right? So we can get some concurrency.
So it can be Hugh and Cornelius and
my wife, right?
and okay, just pulling names out of a hat.
Right. The big difference, though, is that what's important is that the order that the messages are processed doesn't matter. So say it's like me and my buddy are here as workers consuming your messages, and it might be I get one message from you and my buddy gets another message from you, pretty much at the same time. And maybe, so I get message one and my buddy gets message two. Could be message two gets processed before message one gets processed. So if order is important, then this isn't a pattern to be used.
Right.
But what
because
it is,
this is asynchronous, and
it was not only asynchronous, but it's like instead of with point to point, it's the consumer gets a message, works on it, and the signals go give me the next message. So you keep feeding me messages in order. Message one, message two, message three. You're sending those. I'm processing those. I do message one. I signal, you give me another message. I get message two. I signal, give me another message. I get message three, and so on. Right. With this, there could be any number of consumers that are running at the same time. You're sending messages, and all you know is that you're getting, give me another one, give me another one, give me another one. So you're just feeding them as fast as you're getting requests next. But there's some concurrency going on. All the messages that you're throwing out are getting processed, say, in parallel. A lot of them, right? So when they get actually finished, who knows? Because you've got a pool, a potential pool of workers.
So point to point is ideal when we need something processed in order, let's say, or rather, the steps of that should be consecutive.
Right.
Work pulling is when I have work of all kinds to be done and I send it out, or I wait to be invited to send out my work to as many workers as possible.
Right. So say, for example, you're building a shopping cart that ultimately, if the customer says buy, that means, all right, we've got an order to process. Right. Now, as you're building the shopping cart, say you're feeding me every action that you're performing, add item 1, add on 2, add shipping address, add billing address. All of those are messages that I'm consuming, say. And I'm getting them in the order that you built them up. So when the customer says buy, that's another message I get and go, oh, okay, I can process this order. If we had a bunch of workers doing it, it could be that I get the buy message and I process it, but the last item added to the cart, or the last thing before the buy button was hit, is still being processed by another order.
Right.
So it's like the order goes by. I say buy, But then an item comes in. It's like,
Mm-hmm.
that's wrong, right? So something like that.
So that's a good sounding use case for point to point. What's a comparable situation for work polling? I'm trying to think of something. You've got to have a good example.
I think, it could be simpler actions. It's not something that's built up as multiple steps, but it's more like, I don't know, maybe, for example, inventory, grabbing inventory. And, it's just, you want to pull inventory as fast as you can. So you just, you're feeding me requests to pull inventory from the warehouse or something, right? And the order doesn't matter necessarily, because
until the packet, the overall package is complete. Doesn't matter if the tennis ball gets into the box before the shower head, or I don't know where I'm coming up with these, but
and I'm sure
so it doesn't matter. It doesn't matter how the order in which my items that I've bought get packed into the box. Let's say.
Right.
Gotcha. Okay, that makes sense.
But somebody that's really familiar with this process, right, sitting there going, "No, those guys are wrong, completely wrong." There is some flow to it.
Well, I mean, let's have the conversation. I'm always happy to throw myself on the grenade for knowledge.
Yeah, me too.
So the third one is sharding. And what does that look like, and how is that different from work polling and point to point?
Before we move on, just real quick, sorry, but yeah, it is sharding, but there's an interesting player involved with the work polling, and it's a new thing for Akka Type. It's called the receptionist.
Ah, yes, I've heard of this. I'd like to hear more.
Yeah, so it's fairly simple, and I love the way they did it. It's one of these things where say you and I are actors running in different nodes in the cluster, the same Akka cluster, but we want to find each other. We want to be able to talk to each other. So, if we were instances of the same actor in Akka Classic, there was a way that we could do that. And the way we could do that was that you and I both know that we both basically have the same name in Akka. In our path, that I'm on host 1 or 2, and you're on host 1. There's a path to an actor as well, like user / whatever the path is. Well, that path is the same for me. So to build the actor reference to talk to me with Akka Type, you could take my host name and your path and build the URL, and then you could send me a message.
Sorry, in Akka Classic?
An Akka Classic.
Okay.
With Akka Type, that doesn't work anymore.
Okay.
So to deal with that, they came up with this a brilliant concept called the receptionist. So what the idea is that when I know I want somebody to be able to find me in the cluster. So what I can do is I can register myself with a local receptionist. Every node in the cluster has a receptionist. I can register myself, and I can tag myself and say, with what's called the service key.
Okay.
So it's like I'm a whatever my tag is, right? Whatever my key is, and then you want to find actors that have registered themselves with that certain key. Well, you can go to your local receptionist and ask, what actors are in the cluster that have registered with this key, and then you get back a list of all the actor references for those other actors from your local receptionist. So the receptionists are collaborating with each other across the network. Whenever somebody registers with one receptionist in the cluster, it's the responsibility of the receptionist to communicate that across the cluster.
So, and this is when it's the same instance of an actor, or rather, sorry, multiple instances of an actor.
Multiple.
So I know that I'm looking for the same key, or rather the same. I know that I'm looking for myself, for example, somewhere else.
Yeah, in a way,
Okay.
yeah.
Interesting.
And the way we do it, the way we set up as developers is those actors register themselves with a known key, with a known service key, and then that service key is how somebody else can find the actors in the cluster, because the nodes in the cluster
turning on find my friends or find my iPhone.
Yeah.
You can actually put a setting in multiple apps that basically broadcasts your location to whomever you've trusted in your network.
Kinda.
But it's not the same as a registry. It's more like the availability of visibility, if that makes sense.
Yeah.
Yeah.
So
that's interesting. Okay.
Yeah, and then work pooling uses that to in this collaboration, that the worker actors are registering themselves with the receptionist, so that they can be found by the producer.
Okay.
And it's actually the work pooling producer controller that's doing the finding. So it's not, you know, the producer's responsibility, the producer actor's responsibility. So there's a lot of interesting kind of Akka magic, in a way, happening that's out of the box. Another really good example of very nice out of the box behavior that's solving some interesting problems. Like, you know, worker actors can appear all over the cluster. They register themselves with their local receptionists. All the receptionists broadcast this between each other, and the work pooling controller on your end has all this information. So it has the list of what workers are out there in the cluster. And workers can come and go, and that list is maintained, and all that's transparent to you as the producer actor. The only thing you have to be responsible for is responding to, giving another message, all of it, you know, that type of thing. And all the heavy lifting is being done by the controllers. So it's pretty cool. So sharding is more along the lines of sending, being able to send messages from a producer to, it's not, you know, like point to point is like, there's only one receiver. Sharding is where the messages that you're sending are actually intended to be processed by specific actors. And this gets into the kind of the entity actor pattern, which is, you know, part of cluster sharding. But in this case, it's a little bit simpler form, in that, or different form, maybe not simpler, but because our cluster sharding is actually very simple as well for us to use as developers. But with this kind of situation, is like you create a message, and in this message is some kind of ID that says this message is supposed to be processed by an actor that's responsible for processing that entity. Because what you're trying to do is you're sending messages to this other entity, and this other entity, let's say me, an instance of me, you're building up state in me. So it's like you're building up my order, okay? So I'm handling order 1, 2, 3, 4, 5, right? So all the messages that you're sending to your sharding controller, which is on your end, are clearly marked with, yeah, this is for shopping cart 1, 2, 3, 4, 5.
It has to go to this shopping cart, because if it doesn't and it goes to another one, it's going to add an item to the wrong order, let's say.
Right.
Gotcha. Okay.
But the thing is that you're funneling messages for multiple shopping carts through you. You know, you as a producer.
Right. Yeah. So I'm not only dealing with one order at a time.
Right.
Yeah.
So you have other messages that are intended for other actors that are responsible for handling the state of another entity, right? So
I have to make sure every message goes to the right actor at the right time.
And your only responsibility is that every message has a clearly defined identifier.
Okay.
Yeah, and in the protocol of the message that you're
sending. If it doesn't, am I able to receive a message that doesn't have an identifier with Akka typed now? It seems like that was something that was possible in Akka Classic, where, you know, an actor could get a message that the actor doesn't know what to do with it, for example.
It's beyond that, really.
Yeah.
I mean, with Akka typed, you have to, the actor can only receive messages of a well-defined type.
Right.
So it's impossible for you to send messages that don't match this type. And this is the whole strongly typed approach. This kind of takes it down to the data level, that, all right, one of the message types that is flowing through, you know, from the producer to the consumer has to also say that in the message, there is a field, you know, that says this is the ID.
Mm-hmm.
And the data in that field is used to do the flow control.
Right.
Versus just the type. You know, are the types of the messages okay? This is are the types okay, but also the routing is derived from a field that says, yeah, this is for entity ID 42, and this is for entity ID 43.
So if that field is missing, for example, and I receive it, there's some backup plan where I would either send that message somewhere else into a
you couldn't send it to,
no?
you couldn't
So
even
it's
send
this
it
safe.
right. Yeah, you
Yeah,
couldn't even,
wow.
I mean, a compiler would catch it.
Yeah, okay.
Right.
Gotcha.
It would be caught at
getting
that
down
point.
to that.
Yeah.
Okay.
Which is by design, you know, with Akka type, which is very cool.
Yeah.
So,
this is what sharding does.
Yeah. So it's still the work pulling. You know, we started with the work pulling pattern where you're no longer the driver, you're the passive producer, right? I signal to you, give me another message. I signal to you, give me another message. Now with sharding, we are at this point where, all right, it's cool, it's still that pattern, but you have workers on the other side. You're not constrained to a single point to point. You can have many workers on the receiving side that are consuming your messages from you.
Okay.
That will be routed to the right place. And this is a very powerful pattern. And this is, you know, very similar to cluster sharding, but it's its own type of setup. And again, I keep looking at the diagrams to make sure I'm not lying, but so the diagrams are really good that they did.
This is on Akka.io in the docs.
Yeah, in the documentation, there's a whole section under cluster that's called reliable delivery.
Okay.
And there's subsections in there. You know, so I was just going through the documentation. There's point to point, there's work pulling, and then there's sharding, and a bunch of other stuff. But those are like the three big ones. Three really interesting patterns here that are new on Akka type.
So being cognizant of our timing here, why don't we discuss just for a couple minutes about the other couple things that came out in the latest release of Akka. So we've got sharded daemons and distributed pub sub. Which one do you want to, since we were just talking about sharding, maybe how does this relate to sharded daemons or demons?
Sharded daemons.
I realize you can actually pronounce it 3 different ways.
I know, it drives me crazy. Daemons, whatever.
Demons is a little too scary for me.
Yeah, So the idea is that with sharded daemons is these are actors that are there to keep actors alive across the cluster. And what this is used for, one pattern that it was really intended for, is that, say you don't want to use, say, the reliable delivery approach for sharding.
Okay.
You want to do something like that, but it's more custom. So so one approach is that with event sourcing and CQRS, command query responsibility segregation, the idea is there's this concept of projections. And what a projection is and I was thinking about an analogy here, and I think the analogy could be, think of a building. At the core of the building, you know, there's a skyscraper, there's elevator shafts, and that's kind of always at the core of the building. And then you have the facades of the building, the glass, where you can see things. So think of the core of the building being event logs. So you're just adding events, bing, 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 bing. They're just getting stacked up in the core. Projections are a view of that data, but it's stored in a way that's optimal for various types of queries. So I've thought that maybe the building glass facade, you know, like a multi-sided, think of a hexagonal building or something where there's many sides to the building. Each side is a view of your data projected in different ways.
Okay.
To support different queries. So the challenge is that there's some kind of a processing that goes on where you're consuming those events, and you're trying to get them projected as quickly as possible. So one approach is that to subdivide the work and do some of this work concurrently, you have multiple consumers of those events, that whole worker pattern that we talked about.
Okay.
And but the thing is, you want to keep all these workers alive. And through changes in the layout of the cluster. So say everything's running, say we're running on 3 nodes in the cluster, and you've got your they call them read-side processors, is a nice term for them. You've got these actors that are running in the cluster, and they're just happily consuming away and processing events and projecting them as quickly as possible. And then wham, we lose a node in the cluster. Well, as fast as possible, we got to get those read-side processor actors, say, running again somewhere else in the cluster.
Doesn't matter where. It's about recovering the actor, not the node or JVM or something like that.
Right.
Gotcha.
So the sharded daemon process is kind of the helper in this, where we write the code to do the consuming and projecting, as maybe as an actor or a set of actors, and we have this partner sharding daemon that's keeping us alive somewhere in the cluster. And when with the idea is that in the consuming part is, say you instead of having one consumer that's struggling to keep up with the event log, you have multiple consumers. So the approach is you tag the data. So there's maybe tag 1, tag 2, tag 3. All the data, all the events that are created, say, fall into 1 of 3 tags, for example. So you got 3 RAID-side processors that are running that you would like to have evenly distributed across the cluster.
Okay.
And this is what these daemons are doing, is that they're kind of a partner. It's like the controller, the consumer controller and the consumer have a tight partnership. It's kind of, there's this sharded daemon, and say the actor that the daemon is keeping around somewhere in the cluster. I think the general idea is that. I remember working with a customer not too long ago where we had to implement this on our own.
Oh yeah.
It wasn't that hard to do, but it was like, it's a pattern that is commonly done. And this is what the Akka team does. They see patterns of, I had to rebuild it. You're on a different project. You have to rebuild the same thing. And it's a very consistent pattern. They see that and go, hey, we should provide this out of the box. That this is what cluster sharding is.
So this was actually a customer, like a lot of other features I've seen come up through the release path. This was customer initiated. That's good to hear.
In a way, because this is the beauty of the way we do support, where the engineers are directly involved with customers. So the Akka team is always working on things that they're hearing from customers, and it's not just problems, but it's questions as well.
Yeah.
So it's a beautiful win-win type of situation. They're hearing things that everybody's doing. They're taking all this in and saying, "Oh, we detect a pattern here. Maybe we should provide something that'll solve this for a lot of people." And I think that's what came out of some of these things here.
Okay. And last but not least, distributed pub sub. This also sounds kind of unreasonably simple, but it's probably got a lot more behind it.
Well, yeah, it's the concept of a publisher and subscribers is very intuitive. Also like consumer producers, and it really is that that actor, one actor can publish and one or more actors can, or 0 or more actors actually can consume.
At least one. Yeah.
Well, I mean, with pub sub, it's like you publish it and it's kind of like fire and forget, right? You publish it and you're done. And maybe somebody consumes it, maybe doesn't. The same thing even with Kafka. You could have somebody that's publishing something to a Kafka topic. Maybe there's consumers out there, maybe there's not. Who knows? But the publisher doesn't care. And then the consumers are just pulling from that. And this was a feature in Classic, and they just hadn't had a chance to implement it in typed.
Gotcha.
So this was rolling this capability out in typed. So it's just kind of getting some symmetry between Akka Classic and Akka typed. But it really is just, the concept of you're publishing to a topic
Hmm.
and you're consuming from a topic, and is providing it with the more strongly typed features of Akka typed.
That should make a lot of Akka users happy, I think.
Yeah, I'm not sure how much this is used. I know it's being used, and it's definitely a nice thing, feature, and it was just something that they had to get done in Archetype. So
Great. Well, Hugh, thank you for this very educational conversation. At least I was educated. I hope our listeners and viewers also learned something. As Hugh mentioned, everything that you want to read about these topics and more, you can find on akka.io under the documentation tab. The Akka documentation is a fantastic resource. It's really something that you can spend a lot of time reading. And I just was glad to be able to sit with Hugh McKee and get a little more depth and understanding about some of these new features. So Hugh, thanks again.
Always a pleasure. Love these conversations.
Yeah, likewise. We'll be back around soon with some more interesting topics with Hugh. And I wish everybody a wonderful day. Stay safe and wash your hands.